my name is Cameron Krogstad and I am doing compaction for my CE342 final. The format of my video will be similar to a guest lecture. So what is compaction and why does it matter? Compaction is the densification of soil by the application of mechanical energy. Think filling a bucket with sand and hitting the top with your shovel. You also have to modify the water content of the soil to reach the desired soil density. Think adding water to that sand so it sticks together better. The objective of both of these variables is to improve the engineering properties of the soil mass so you can build that perfect sandcastle. The result of this can reduce and prevent detrimental settlement of soil, increase the soil strength and slope stability, increase the bearing capacity of subgrades, decrease permeability, and control the swelling and shrinking of soil. The main process of compaction on site is as follows. First, fill specifications are provided by an engineer. Then, fill material is imported and engineered with moisture and mechanical energy. Testing is performed to confirm specifications are satisfied lastly. So how did modern-day compaction come to fruition? Well, it was developed by Ralph Proctor in 1933. Hence the Proctor lab test, and it was created as a function of dry density, water content, compactive effort, and soil type. Here you can see the variables of the standard Proctor lab test and an example of what it looks like. The mold is filled with soil in 3 levels and compacted with 25 hammer drops at each level. The mass and volume of the soil is recorded. The soil is then oven dried to determine the water content of the soil, and the dry density is calculated using the soil density and water content. What is the compaction curve? The compaction curve is used to determine the optimum water contents and maximum dry densities of soil. There are at least 4 tests per curve, each testing different water content percentages. The curve is shaped this way because water lubricates the soil as water content increases, but then water replaces the soil and the soil density becomes higher than the density of water. In specifications, the typical maximum dry densities are 1.6 to 2.0 megagram per cubic meter or 100 to 125 pounds per cubic foot, and the typical optimum water content is between 10 and 20%. Here we can see the compaction curves of various soils from class. The one we will see later most closely resembles curve 2 of a well-graded silt. I will now transition to my experience with compaction in the field. In the construction industry, soil is king. I've had the opportunity to work on different projects that contain different types of soils over the past 2.5 years. The Mazda Toyota manufacturing facility in Huntsville, Alabama, a Toyota factory expansion in Jackson, Tennessee, an EV battery facility in Commerce, Georgia, a Boeing facility in Charleston, South Carolina, and a BMW plastics supplier in Anderson, South Carolina called Eugen Wechsler. At each of these sites, I was able to be on site each day and monitor the construction of the buildings, the effect of the weather on the soils, and how the contractors dealt with each problem. Geotech testing is a part of every single construction job, and the jobs would be a disaster without it. I will be focusing on the Eugen Wechsler project and the Toyota factory expansion to explain the importance of compaction for each of these sites. I will also show how we employed multiple concepts we learned in this class. The tests that I was able to witness and review on each of these sites included a field proof roll test and a laboratory Proctor test, which is used for specs by ASTM D69812. The equipment used on site were sheep's foot rollers, smooth drummed vibrating rollers, and trench rollers for stormwater trenches and backfilling underground piping trenches. A proof roll is done by loading a dump truck with gravel and slowly driving over the area deemed for testing. If there is pumping of the ground during the test, the area needs more compaction and a retest of the proof roll. Using these tests, we could determine whether compaction was up to the design specifications. While I was in Jackson, Tennessee, I had the opportunity to be there while they were doing fine grading for the interior concrete slabs and for the asphalt road on the exterior of the building. My picture of a sheep's foot roller and tractor scraper are shown in the bottom right. For each respective part of the grading, the soil had to be compacted to different specs. The interior slab portion had to be compacted to at least 95% soil compaction, per the geotech design specs. The exterior asphalt portion had to be at least 90% soil compaction. The compaction percentage is based off the void ratio in the soil. The higher the compaction percentage, the less void ratio. This compaction is important because it will make sure that the concrete or asphalt does not crack or sink. The water content of the soil is also important for this similar reasons. The proof roll was done after the fine grading for the exterior, and the compaction failed at multiple points. As you can see, there is clear pumping in the proof roll I witnessed in the top right picture. Once the proof roll and the lab soil proctor test have passed, the soil and gravel is now ready for asphalt and concrete application. The left picture shows an asphalt subgrade that has passed a proof roll and is ready for asphalt. For the Eugen Wechsler expansion project in Anderson, South Carolina, I will show the type of soil tested, fill specs, and show the results from actual proctor tests. This will give a good example of how what we learned in this class really has an application to the construction of buildings. Here we have a lab compaction characteristics of soil report. This is for an on-site fill stockpile, and it was tested for maximum dry density and optimum water content. This also shows an example of the compaction curve we spoke of earlier. This here shows the type of soil that we were testing and a map of the site. It is actually a red-brown clayey silt. The specs of this project require a water content between 22.6 and 28.6%, and a minimum compaction of 95% for the concrete. Here is an example of a field density test report. This shows the wet density, water content percentage, dry density, and the percent compaction of the soil. As you can see, the soil passed all of the specs and project requirements. I've appreciated the opportunity to learn the calculations, history, and engineering behind these reports that I have reviewed and been a part of in the multiple projects I have worked. I can't wait to apply even more of this knowledge in my future projects and career. Even more important, you now know how to engineer the perfect sandcastle on your next vacation. Thank you for a wonderful semester, and check out our website.